Hey, guess who? It's me. This is the first of the two labs about the coastal environment. In this particular lab, what I'm going to be going through and what you are going to be working on is the ocean itself, as in actually the seawater. One of the ways that we can describe the ocean or seawater is by describing the salinity of the water. This means the dissolved solids, especially the salts within the water. You're probably aware that water is referred to as a universal solvent, which means that you can dissolve anything that can naturally be dissolved in water. You know this yourself. You take a glass of water and you take a teaspoon of salt and you stir it in. The salt disappears, but of course it's still there. Take a straw, stick it into the water and suck on that straw, and you're going to realize very quickly that there is indeed salt in the water. But the salt is just dissolved, making what's known as a solution. So anytime you dissolve something in water, you are making a solution. You want to take a guess before I go any further? You've probably all been out in the ocean before and gotten a mouthful of it. How much of the ocean on a percentage basis is salt? Take a guess. Go ahead. I'll wait. You in the back over there. Go ahead. Raise your hand. There we go. No, you're wrong. Average oceanic salinity is 3.5%. That's what it is, which means when you take a drink of that ocean, 3.5% of what you're tasting is salt, believe it or not. So it's mostly not salt. But salt, of course, is very salty. There's a couple of ways that I want you to be aware of that we can write this. 3 ways, really. 3.5% is one of the ways. The most common way that we're going to use is this second one, which is 35 parts per thousand. And you write it just like that. 35, then 0/00. That means 35 parts per thousand. That's a very common way to describe oceanic salinity. Another way is 35,000 parts per million, which is written just like what you see there, 35,000 ppm. But we're overwhelmingly going to use 35 parts per thousand. I'll probably occasionally reference 3.5%. If you take a look here, you can see what the primary salts are that are in the ocean and their percentages. Now, if you look at chloride, let's just start with the most prevalent of the salts. Notice on the far right-hand side it says 55.03%. So what that means is of the 3.5% that is salt, this means that 55% of that 3.5% is chloride. Then you can see the second most prevalent is sodium at 30.59%, sulfate, magnesium, calcium, potassium, and so on. Which is the most? Well, chloride is the most. 55% of the dissolved material is chloride. Because of that, we can also describe the chlorinity of the global ocean. And indeed, we're going to do that. You're probably aware that sodium chloride, NaCl, is table salt. These two things, the most prevalent salts, combine together to make this thing that we call salt, which is, of course, a very stable thing. What are the sources of the salts? Is that what you asked me? I'll tell you. Well, one of them is runoff. So a river, or water in general, flows across the land area, and as it does, of course, it's going to dissolve material in that water. And then when that water dumps into the global ocean, it brings that dissolved material into the ocean with it, which then mixes over time with the greater ocean. Another source is outgassing. This occurs when the Earth expels heavy salt-laden gases from its interior, and it does this through volcanic activity. It's especially prevalent in sites of crustal divergence, which of course when the crust pulls apart, that opens up the surface area, or in the case of, for example, the Mid-Atlantic Ridge, it opens up the ocean to whatever's inside the planet. Hotspots, which are also volcanic, and when they're out in the ocean, of course, the material is going to come into the water and be able to dissolve, just like it would with crustal divergence, and in areas of convergence where there's volcanic activity. Most of the salts dissolve, though, before they reach the surface naturally, and they go into the water, and have been doing this for a long time. There are 3 ways that we determine the salinity of the ocean. 1, evaporation of seawater, which we're going to do. 2, chemical titration, which we are also going to do. And 3, conductivity of seawater. So evaporation of seawater means exactly what it sounds like it means. You take a certain amount of water, you know how much it is, you've taken the sample out of the ocean, you put it into an oven, You dry it out and you see how much salt residue there is, and you compare these two things, the original quantity with what you get after you dry the water out. Chemical titration happens when you take silver nitrate, put that in the water, and then what it does is it turns a color that then allows you to know percentages. This is similar to one of my earlier videos where you saw me doing this with tap water. Conductivity of seawater means this: the saltier the water is, the better it is to conduct electrical currents. So we're also going to do that as well. There's a couple of terms I need you to be familiar with: brackish and brine. Brackish water means this. It means that the water is less than 3.5%, or less than 35 parts per thousand. You find in the global ocean water that is brackish in 3 types of places. Here's the first one: at the mouths of major rivers. Can you guess why that would be? Because where a river empties into the ocean, it's infusing fresh water into the ocean, and that dilutes the ocean. There are 2 others. Can you guess what they are? Okay, here we go. High latitudes. So that means very far north and very far south. Do you know why that would be? Because of melting glaciers. Glaciers are fresh water. That will have an infusion of fresh water into the global ocean, and that will dilute the salt water. And the equatorial zone. Do you remember the equatorial low pressure system? You have hot rising air. Hot air holds more water, and that causes a lot of precipitation. So you get a freshwater infusion also coming out right along the equator out of the equatorial low pressure system. Brine water happens when the percentage is above 3.5% or above 35 parts per thousand. This is typical in one type of location: in semi-enclosed seas in the subtropics. Remember, the subtropical high pressure means this: clear blue skies, dry air, the air is descending, not a lot of clouds as a result of that, high evaporation rates. Semi-enclosed seas, because if the water is not mixing with the global ocean, it allows for even more evaporation. This would be common in places like the Persian Gulf, the Red Sea, the Mediterranean Sea, and on our side of the world, the Gulf of California, also known as the Sea of Cortez. We're also going to take a little look at seawater density. Salinity and temperature play roles in density. Can you guess what they are? Just think about temperature and the way it worked with the atmosphere. Seawater is 2 to 3% denser than freshwater. It's because of the salt content. And in fact, fresh water will, in certain circumstances, all things being equal, float on top of salty water. Cold water is heavier than warm water, just like cold air is heavier than warm air, right? Cold air wants to subside, warm air wants to rise. The same thing happens with water. Cold water wants to subside, warm water wants to rise. So cold, salty water will result in a heavy, dense, subsiding water. This also, by the way, helps drive ocean currents. All right, that's the setup. Now off to the math.